Nick and I are honored to welcome you to the 2020-2021 SIOP Machine Learning Competition. At a real high level, Nick and I will cover what this competition was all about. The winning teams will present and showcase their approach and winning solutions. We'll close with a panel discussion. Rapid innovation is automating a lot of what IOs are doing and a lot of what many disciplines are doing. If we don't adapt as a field, we will fall behind, we'll become less and less relevant, and eventually will fade away. To spearhead innovation requires that we allow the best ideas to come forth regardless of source, a true meritocracy. To enable a meritocracy, we have to tap into the broadest range of ideas. And this requires that we open source everything. We need open data, open registration, automatic ranking so that Nick and I don't have to score the thousands of solutions that come in. And then we want to open the winning code solutions. This creates a living entity. As new methods arrive, apples to apples comparisons can be done on the benchmark that is created by this data and the winning team's scores. So a little bit about our open registration. This year, because of COVID, we expanded it, and it was actually 2 years. We had over 200 teams register. With about 3 people per team, that's 600 people participating in this year's event. The number of submissions of actual machine learning solutions that we scored or processed was over 1,500. For 60% of people, this was their first ever machine learning competition. So you can see that a lot of people are getting their first hands-on experience with data science and messy data through this. We really bridge the academic practitioner divide with about 50% of teams originating from each. And likewise, education background was diverse. This is not a PhD only event. The programming languages used were by default open source. This year, more than last year, we see an uptick in the use of Python. And interesting to me and encouraging to me is actually the quarter of people that used both. The competition was hosted on Eval AI again. This is a team that open sourced their competition platform. If you've ever tried to host something on Kaggle, you realize that it costs a lot of money. And that's why it's great to have this alternative. The portal looks and feels pretty professional for something that is free. And it allows teams to register, to participate, to submit, and automatically get scored and see the public leaderboard. That's this right here. Of the 200 teams, about 60 of them actually interface with the portal to submit real solutions. Sometimes people will develop solutions but not submit them. All the solutions derived from this year's competition will be, well, all the winning ones will be open sourced on GitHub and available to anybody and everybody that has access to the internet for free. This includes the entire reproducible code set because everything was done in open source, along with the presentations, this recording, and the data. Let's talk about the data. This year's data is unprecedented. I was told by respected colleagues that it could never be done to open source real employee selection data. We are humbled to work with Walmart to open source this data set of about 50K employee selection records. And the objective here was to maximize both validity and fairness in this pre-employment selection assessment.
Thanks, Isaac. So what was the goal of this year's competition? In the inaugural machine learning competition that was hosted by Dan Putka and Alexander Schwal, they were able to secure a great data set of internal organizational data. And the goal there was to use that data to predict employee attrition. In 2019, we entered the world of natural language processing to see if we could use situational judgment responses to predict self-reported Big 5 personality traits. This year, we decided to see if machine learning could tackle arguably one of the most difficult problems of all in our field, namely developing an algorithm from a selection battery that could predict performance and turnover simultaneously, all while being fair. These criterion often are at best unrelated. And in this particular data set, they were correlated at roughly 0.1. As a planning team, we were faced with a difficult problem ourselves. How can we generate one aggregated score to represent how well an algorithm accomplishes the goal of this competition? We spent many hours and met with many, many individuals to discuss this. In the end, we ended up with what you see below. We ran a simulation of over 4 million potential combinations to settle on a distribution that was supposed to fall somewhere between 1 and 100. And you'll see we were off a little bit in some of our assumptions. Our final score is a combination of overall accuracy minus unfairness. We operationalized overall accuracy as a weighted combination between the percentage of top performers the team hired, percentage of hires that were retained, and because both of those are important, we weighted the intersection of those two groups the most heavily. Meanwhile, unfairness was the absolute value of 1 minus the adverse impact ratio times 100 to put it back on that same scale. For this competition, our goal was actually true fairness, not simply not violating full-fifths. So as you'll see from the final scores, the top teams were right at a selection ratio of 1-to-1 in almost all cases. A little bit about the data. As Isaac mentioned, David Futrell and Walmart were gracious enough to allow us to use probably one of the biggest and most complete validation data sets I've ever seen. These data were part of a large-scale criterion validation study for entry-level store associates. There were some small modifications made to the data set as part of this competition, namely the PII was all removed, and protected group was a contrived variable that was actually a surrogate for ethnicity and gender together. Item content itself was removed, but the relationship between the items and the scales were maintained via naming conventions. The data set included 12,390 supervisor ratings of job performance and 48,602 indications of turnover at our predetermined time and position. 44,102 individuals were included in the training data set, and 2,250 were included in both holdouts.
So what does all this mean? There was a community of over 200 teams that essentially worked together on one of the largest employers' data sets to solve one of the toughest and most applicable problems in our field, bringing fairness and validity to selection algorithms. You know, there's a lot of conversations about bringing fairness to AI, but as the age-old adage, I think from Facebook, is that code wins arguments. We want to have more informed conversations, and we want to look at what are we missing as a field to solve this fairness issue. We wanted to make the code available to all so that no selection firm has excuses not to be as fair as possible. Now, this was a true north. I don't think it really achieved this, but it was at least a goal. And again, this results in a living project where collaborators will get the opportunity to continue to innovate. This means grad students that we don't even know that are grad students might come out and build something that is better than everything we've seen yet.
So I wanted to take a quick look at the overall aggregate data. One thing I always find intriguing is the distribution of the scores. You see a bit more variety in the public leaderboard, which kind of makes sense as that's the opportunity you have to try a bunch of different strategies. The private leaderboard was limited to 5 submissions per team, so they've typically settled on their algorithm and strategy by that point. One thing I did notice, and I hinted at this earlier, was that in the public leaderboard, there were a few negative scores, which means my assumptions in the simulation about the max adverse impact ratio were a bit off. Let's go to the next slide. Yep. Another thing I wanted to look at was if we treated some of these individual goals in isolation, what were the best predictions? The team that had achieved the highest percentage of true top performers hired in the public leaderboard was team procrastination with 64%. For comparison, the median prediction across all submissions for this was 60%. For true retained, there was actually one team that was all alone. It was Sam Cannon's student loan debt. They achieved a percent correct retained of 72.6%. Meanwhile, the median prediction was 57.8%. This team had 30 submissions with higher percent correct than any other team, and they actually had a really good adverse impact ratio on these submissions. So if you want to improve retention alone, you might want to reach out to this team. The intersection was interesting, and there were two teams that achieved a percent correct here of 63.33%, while the median was 59.6%. So you can see this one was much tighter than some of the others. The most common selection ratio was actually a perfect 100%, with 19 separate teams achieving this. So on to the good stuff. How did everyone do and who won? The public leaderboard's top 4 were Go Ahead, Make My Data, #GreedyCow, Don't Ask Us Why, and Data and Confused. But the entire top 10 was very close to one another in the public leaderboard. But at the end of the day, the goal of this competition is generalization. And as all of us know in machine learning, making adjustments several times to optimize for a holdout set itself does have the potential to lead to overfitting on a new set of data. This is, of course, the purpose of the private leaderboard. On top of the private leaderboard, there were 2 teams that were neck and neck, and the teams in spots 4 through 8 were also very close to one another. So we had some really tight races here. So without further ado, let's introduce the top 4 teams. In 4th place with a final score of 60.72 was Go Ahead, Make My Data from Colorado State University. In 3rd place with a final score of 61.09 was RHDS from Red Hat. In 2nd place with a final score of 62.5 was Axiom Consulting Partners from Axiom Consulting Partners. And in 1st place with a final score of 62.53 and a returning winning team is Team Procrastination from Bowling Green State University. I know we're on Zoom, but I'd like to give a quick round of applause for the winning teams and also thank everyone that participated this year. Now I'll go ahead and turn it over to the teams that we should be hearing from. And we'll start with the 4th place team and Go Ahead, Make My Data. We can hear about their strategy and their learnings.
So my name's Josh. I'll be representing the team Go Ahead, Make My Data. I was joined by my older brother, Jason, who just finished his master's in computer science from Georgia Tech, as well as 3 students from the CSU IO program, Steve, Kelly, and Shaylin. And much of the novelty of our approach came from having someone outside of IO on our team. And I'll highlight that periodically with, I asked Jason this, and he said that. But before going on to our approach, I'd like to take a second to recognize Isaac and Nick for putting this competition together. I'd also like to highlight a statement Isaac made in a 2019 SIOP article. Science should be transparent, it should be inclusive. So from designing fairness into the performance metric of this competition, to opening it to the community, to organizing this presentation and posting it for others to view later, to open sourcing the data and the code, I think Isaac and Nick are really living up to this statement. So to begin the overview of our approach, I wanted to start with a slide I've seen in past winners' slides highlighting diminishing returns on effort spent. Here, the large circle on the left represents our first approach, and it's a score on the public leaderboard. It had some machine learning inspiration, and even though we used code to pull it off, I believe it could be recreated without code in something like SPSS. The small circle on the right represents how much bigger or how much higher our score rose once we really started applying code and what most folks think of when they think machine learning. And it's an important tiny dot. It's why I get to present today. But it also makes me hope that we can make some space for some of the other teams to share, perhaps on GitHub, perhaps elsewhere, because I'd be surprised if there wasn't a team out there with something important to say, but was just one tiny dot short of getting a chance to share it here. So moving on to the big dot, our initial approach, we started with a couple decisions to get set up. First, regarding missing data, an easy to implement approach is just to impute the median, so we did that. And regarding how to handle predictors, Putka et al. In 2018 had good success treating all of the items from an 80-item biodata survey as individual predictors, so we did the same. There are around 120 items and some reaction times. They all became predictors. We just dumped the data into our models. So the first, Jason, what do we do question was, how do we handle multiple outcomes? And as a follow-up, what if we predict those outcomes and get hit with a big adverse impact penalty? I was thinking things like make a criterion composite, drop predictors with large group differences, somewhat standard selection stuff. Jason's suggestion, which is, sorry about my dog, which is what we went with, is a model voting system. The ultimate decision to hire is made based on multiple models casting votes, in a sense. Specifically, we had 3 outcomes from the data, as those identified as high performers, retained, and of a protected group. We also created a new outcome of those who were both high performers and retained, since we thought they may be unique in some way. We used all of the predictors to estimate separate logistic regression models to predict these now 4 outcomes separately. Each model could then provide a probability that a new individual was from some valuable group. We could combine these probabilities into an overall predicted value of hiring someone. Then we moved to the development set, tried a handful of weights. One set of weights put us at a decent spot on the public leaderboard. So we stuck with this general approach and tried to improve upon it. So we implemented improvement in steps, the first being that we wanted to swap logistic regression with some fancier algorithm. So I go to Jason, express dismay over needing to run models and tune them and run other models, to which he says, have you heard of AutoML? So AutoML, or automated machine learning, is an approach that recognizes that much of machine learning is navigated through trial and error, like selecting an algorithm and tuning it. So why not have those trials set up and evaluated by a computer? So what does this look like to navigate? We used a package called Teapot. What does this look like to navigate in Teapot? And I wanted to put all of the relevant code on a single slide to highlight that this is pretty approachable. Hopefully you can see this all right. First, setting up Teapot to make some decisions for you. Different AutoML packages take different approaches to navigating the number of decisions to evaluate. Teapot uses a genetic algorithm. This is set up in the first line displayed. Setting up pipeline optimizer here using the Teapot classifier argument, or function rather. Specifically, it sets up a population of different approaches, here specified as a population of 20. It evaluates those approaches using some cross-validation strategy, here just one round of 5-fold cross-validation. And then it takes the best approaches from the current population to use as a starting point to randomly tweak and populate a subsequent generation of approaches. And here, just 2. More generations and larger populations are used for more complex problems. So in the next line, pipeline optimizer fit, you just tell Teapot where your predictor data is, as well as your outcomes. And finally, Teapot will output what it thought was the best approach to a Python script for you to further tweak. But full disclosure, I just took what popped out of the box. And then in the output, we can see that for high performer, it found that a random forest was the best approach to classifying who was a top performer. It did some variable scaling. This is scaling variables from 0 to 1. And then it gave me a series of tuning parameters for that algorithm. So at this point, we swapped logistic regressions for machine learning methods found using Teapot. We then needed to assign weights to the predicted probabilities and settled on a rational weighting approach for all models except protected group. And this rational weighting approach was based on expectancy value theory. So how much a model's vote should impact a hiring decision should be based on 2 things: expectancy, or how probable an outcome is based on a model's prediction, which we quantified using the accuracy score from each model. In the picture is the cross-validated accuracy score in predicting high performer. The other thing is value, how valuable an outcome is, which we determined by the parameters of the competition. Thus, we can combine model accuracy and the competition parameters for a given outcome to yield a weight for that model. The weight for protected group was not found as elegantly. It was found by submitting to the development set and increasing or decreasing that weight until we landed on an adverse impact ratio of very close to 1. And then finally, we didn't get a chance to reevaluate imputation or alternative ways of handling the predictor data before the competition closed. Bit of an epilogue to our approach. In submitting our test submission, we had 5 attempts, and I used them pretty intentionally. So I mentioned in the last slide that we fudged the protected group weight to where it would be best for the development set. which fitting that weight to the development set still leaves us open to a protected group model weight that isn't the most generalizable. You can see that here in our first test submission using that weight. However, we had 5 test submissions, and I knew how this weight would impact our overall score, increasing and then decreasing. So I made 2 more submissions at high and low weights to be able to fit a trend line, use this line to find the weight that would yield the highest possible score for our model in the test set. So this also isn't the most generalizable weight. Perhaps a good one could be found using some sort of cross-validation scheme with the training data, but our approach had this neat trick, so we used it. To conclude, I'll share some reflections we've had throughout the process. First, it definitely felt weird to predict protected group in our approach. We'll probably talk about this more later. But the more I think about it, the more I think it may be a good idea. Our hiring models are regularly influenced by diversity considerations, whether formally estimated or not. Whether it's Pareto optimal weights or dropping predictors with large group differences, we modify our predictive models by indirectly considering diversity. So why not consider it directly? Something predicted directly will likely be more accurate than something indirectly hoped for. Second, this competition makes me think about the value of algorithm general techniques. Picking on Pareto optimal weights again, and perhaps the underlying idea can be generalized, but in its current form, it binds the user to ordinary least squares regression. Alternatively, whether it's a model voting system or something folks may already be familiar with in dropping problematic predictors, some techniques don't bind you to an algorithm in quite the same way. And I think it's important to consider as algorithms advance, we don't want our ability to achieve fairness to become outdated. Lastly, be lazy. I'm not sure how Isaac discussed this, but I think being lazy is good for inclusion, specifically accessibility. Tools that are enshrouded in unnecessary code behind paywalls, et cetera, are hard to access. Tools that are designed to be user-friendly or lazy, as I'm saying, do invite more people to use them. And I saw this in Teapot, where it's easy to get up and running. There's plenty of open source documentation to dig under the hood if that's what you want to do. I think being open sourced and user-friendly, at least initially, go hand in hand with accessibility and inclusion, which brings us back to Isaac's sage wisdom from the start. Science should be transparent, it should be inclusive. So with all that, thank you for giving me this opportunity to speak. And thanks again, Isaac and Nick, for making this all happen.
Brian?
Wow, awesome. Thank you, Josh. Go ahead, Nick.
Yeah, no, that was great. Turn it over to Brian and team RHDS. Yes.
Perfect. So I'll just kind of dive right into it here. So here's a little bit about kind of what I would like to discuss. So I think I really wanted to kind of start this presentation with a little bit of more of a philosophical question, which is, are diversity and inclusion and machine learning on a collision course? And the reason why I sort of asked that is because, as many of you I'm sure know, both of these have sort of been rising forces concurrently in sort of our modern times. It's just to kind of set the scene a little bit. As of 2018, despite comprising almost 50% of the total workforce, women only account for 20% of board of directors in Fortune 500 companies, and people of color only account for 14.4% of boards of directors. Moreover, within 25 years, people of color are projected to comprise a majority of the US population, and correspondingly, the US workforce is projected to become even more diverse over the next decade. And so as a result of these changes, and I think just a more general kind of contemporary awareness of the necessity for fairness, organizations have made large investments into diversity and inclusion initiatives, including the emphasizing the recruiting of diverse candidates and creating more fairness in selection systems. Meanwhile, over the same time, we have again sort of this rising force of machine learning. I think machine learning we could spend all day on how to define it, but I think in this context, I'm sort of defining it as using a predictive algorithm trained on data with a known outcome to create predictions on data with an unknown outcome. As I mentioned, machine learning has become more pervasive across all industries and society more broadly. Machine learning techniques and algorithms have been shown to have the propensity for bias across a variety of applications. Bias really can mean a lot of different things, but in the context of fairness and selection, it can certainly mean bias in terms of outcomes against people of protected classes in this case. And while there has been some documented use of machine learning in human resources, overall usage is still low, and there are many opportunities to employ machine learning techniques in an HR environment. And so again, my point sort of is that we've sort of had this rise in these forces simultaneously, and we really see them kind of coming together to a head. And I think that the competition sort of embodies that coming together. And so I think really the question to think about as we go through all of these presentations really is, how can we as practitioners responsibly employ ML techniques in HR generally, and specifically with regards to selection, to reap the benefits of ML while simultaneously avoiding bias and any impending quote unquote collisions. So obviously Nick and Isaac went over the topic, so I don't need to cover this in too great a detail. But what I will say is that my general approach was to predict each outcome independently, and then use those independent predictions to create a sort of weight optimized final quote unquote score, and then rank based on that, and then hire kind of the top ranking of those. And obviously in this case, because we're penalized for adverse impact, the weight optimization both needs to account for making the best hires, but also the most fair selection system. So I'll get into, obviously I think in a lot of cases like this, I would always kind of say, refer to the code. So I would say, for more specifics, you can definitely look at the code on GitHub. So I'll try to kind of cover these somewhat high level. But in terms of categorical variables, we had the situational judgment test items, bio and biodata. And so my approach to deal with those is to end up essentially dummy coding them. And what I do with those is I initially hot encode them, which creates one column for each category, then remove values that occur less than 5% of the time, and then also removed perfectly correlated values. And so really what this does is it creates a referent group where those removed comprised of those removed categories. Also, missing data is also treated as its own category, but there were no variables that had more than 5% missing data, so they ended up missing data just ended up becoming part of the referent group. And male and female used as a predictor was not actually in the data, but I think that this example just kind of shows roughly sort of the approach. So obviously we start with one column, which expands to two, and then in this case, male and female are perfect covariates, because in this case, every time someone's a female, that they're not a male. So it's really redundant information to have that, so that ends up getting removed. And then in terms of the numeric / interval and ratio variables, those were comprised of the personality scale, the scenario items, and time items. So centered and scaled those. I used multivariate imputation for missing data. And I also experimented with principal components analysis. But as Josh mentioned, it did seem like the items did appear to be relatively independent of each other and exhibit a solid discriminant validity. So that actually was not used in the final solution, and it did not reduce the number of dimensions by much. Another thing I experimented with that was not used in the final solution, but I do think is worth mentioning, is the high performer outcome was a little bit imbalanced. There were approximately 40% of the data were considered high performers. And so I experimented with SMOTE resampling, which stands for synthetic minority oversampling technique. What this basically does is it creates synthetic observations of whatever your minority category is to make the data more balanced. But what this ended up doing in practice was it actually decreased the data sensitivity and increased the specificity, making the predictions more extreme. Because for these predictions, specificity was already quite high. So that didn't seem useful to me to use in the final solution. So in terms of the modeling, as I mentioned, I predicted each outcome independently. I used all of the predictors as well. I initially tried without the time fields, as it showed that there may have been some bias towards protected class with those fields, but excluding them substantially reduced the prediction quality. For modeling, I used XGBoost. Surprise, surprise. And obviously, not everyone used XGBoost for this, but it's a pretty common approach, I think, for these competitions. I used a random grid search for the cross-validation hyperparameter tuning. I used 50 iterations. What's interesting about that is I actually used more iterations on other submissions. I tried 102, 150, but they didn't perform quite as well. I took the average of the top 5 models based on the hyperparameter tuning, and then I also used the 95-5 train test split. I think in general, when you're deploying a model, you do, I think, want to use more of your training data than when you're initially just kind of evaluating it. But I think especially for my approach for kind of creating the weight optimization, I think it was useful to have at least some thing of a holdout. So this seemed to be the kind of the optimal approach. And I just want to give a shout out to the OG TikTok function. This TikTok function came out well before the current TikTok we see nowadays, but it's a very useful function for any type of anything that's going to require heavy duty process time, because it allows you to sort of look at how long it takes to process. So definitely a very useful function when training machine learning models. In terms of the evaluation, I think there were sort of 2 parts to it. I think, in general, when building a model, we always sort of go through what was the first part, which is just kind of assessing the prediction quality on your true training data, which is the data used to train the model, and then evaluating how well those predictions generalize to a holdout sample, which is all from the quote unquote original training data. And then my main methods of assessment for that were AUC, which is area under the curve, sensitivity, and specificity, which I think are quite typical for logistic regression style outcomes. And then the second part of this was really, I think, kind of the unique part about this competition and sort of the interesting part. As I mentioned, my approach was to basically predict both outcomes independently. I actually did not predict group membership, which I think a lot of the other teams did. But basically, again, using each of those predictions, the idea was to basically simulate all of the different weights that you could have between those 2 scores to create a final score to rank the holdout data to sort of create the quote unquote hires. And what I mean by that is basically, in theory, you could have a situation where you give the weighting only to one predictor or the other, or kind of anywhere in between that, if that makes sense. I think, again, that if you look at the code, it'll probably make a little bit more sense. And then, as I said, I just ranked by the final scores and then hired the top half. One other thing that I sort of found to be an interesting consideration here was, of the training data that I'm using to build and hold out to kind of test the results, which of those components of data should I be using to create the weight optimization? For example, and because there's I use what's called partition-based sampling to do the train and test splits, and so you're going to have different people in your training and test data potentially for each of your outcomes. And so that created a situation where if I wanted to create the weight optimization only based on people that appeared in the test set for both outcomes, it resulted in a fairly low sample size. But then also, if I only use people that appeared in the training data set for both, then that might result in a situation that doesn't generalize super well. So actually using all of the IDs across both training and test sets ended up kind of being the optimal approach there. And just so this makes more sense, this is not what I ended up using for the final result, but this just, I think, again, kind of illustrates my approach. So in this case, again, we've got 4 hypothetical people that we need to hire 2 of them. And so in this first example, we gave all of the weight to the retained prediction. So you can see how that influences the final scores. They're identical to the retained prediction, and then it's ranked accordingly. And then in a second example, we could also change to weight it where we give most of the weight to the performance, and then we can see how that changes the final score. And again, my approach was to test every single combination between 0 and 1 and going up by a 0.01 iterations. In terms of the final results, like I said, I used all of the training data together to create the weight optimization. I gave and retain ended up having a weight of 0.02, top performer 0.98, and that when I tested that on the training data and kind of replicated the accuracy based on hires, that ended up with a score of around 70, which in the dev leaderboard that was 59.94, which was like 14th. But then in the final leaderboard, it ended up being a little bit, it seems to generalize a little better to the final data with the 61.09. So just some brief conclusions here. Despite varied approaches, I believe none of the winning solutions violated the 4/5 rule, which I think is really exciting. But I also think that, obviously this task was designed in a way to heavily penalize adverse impact. I think it's always important as practitioners, I mean, this goes without saying, of course, but to ensure fairness in any models that we build. But I also think that really this is an opportunity for us where we can use these techniques to be actually better than legal requirements. And I would not, none of us I think would be presenting today if we had just barely met the 4/5 legal minimum threshold. So I do think that one of the takeaways is that we as practitioners can definitely do better than the minimum legal standards. In practice, I do think it's worth mentioning that there are a number of additional steps that should be taken, such as individual item analysis and looking at different results kind of within the different protected, unprotected classes. And just again, adding this, in my opinion, machine learning techniques and their responsible deployment with coding in R and or Python must become part of IO site graduate programs, as we are already competing against other fields for these types of roles. I think that really is imperative. So again, to go back to the first question, are diversity and inclusion in machine learning on a collision course? I would say not necessarily, and I think we have a unique opportunity as experts and practitioners in HR to emerge as leaders that drive the fusion of D&I and machine learning into the future in a responsible and fair way. Thank you.
Thanks, Brian. It was awesome.
Thank you.
Next, I'm going to turn it over to Ian and Robin and Axiom Consulting Partners, second place team, to discuss their strategy and kind of their thoughts.
Thank you very much. I'd like to echo the other teams here and thanking both Isaac and Nick for putting this all together. It was a Herculean effort to get the data set in place and get the leaderboard set up, and we're very grateful for the opportunity to compete. What we'll be talking about today is sort of the method we came up with. We decided to call it Karma. Robin loves to come up with acronyms first and then decide what they mean, so you'll see what that means a little bit later. And in terms of the team that we actually had working on this project, it was pretty diverse, both from a background perspective and also sort of an organizational perspective. Myself, I'm a senior consultant with Axiom Consulting Partners. We're a small consulting firm based out of Chicago. We have Goran Kulyanin, who is from DePaul University. He has a background in psychology. And then Robin Burke out of University College Boulder, background in computer science, artificial intelligence, and in recent years has taken a large interest in the question of fairness and fair machine learning. So we get a lot of different perspectives on this question. As we've discussed before, the actual data set itself, it's kind of a unique challenge to be looking at trying to answer questions of fairness without understanding what any of the questions, we have a lot of metrics, but we don't understand what the questions were. So in a lot of the literature, if you understand what the question is, you can make certain assumptions about the features that are given, do individual analysis on each of the features. We didn't have that luxury, so we sort of had to treat our features independently. And additionally, we understand that the features the sets were created through stratified random sampling. but the holdout sets were variable. This is the reason we saw different results on training and test sets. And that led to a situation where the same prediction system, our modeling system, would have completely different results on the two training sets. So our best test submission, or our first test submission on the test data set, we got a 59.3, and this was actually a full 4 points higher than the exact same prediction system with the exact same parameters used on the training set. Finally, the percentages of retained and protected group vary when calculating the percentages in the subsample of the training data, consisting just of high performers. So as we mentioned earlier, the high performer data set was not the full data set. So we had only about 20% of the full data had performance data, which led to a unique problem of trying to if you're predicting high performer, you either have to impute for the remaining 80% of the samples or create two separate models for predicting high performer and retained, which is actually what we ended up doing.
All right, I think I'm up next here. And I think the big picture to take away from this slide is really, and this is kind of goes back to the acronym candidate ranking through multi-model aggregation. We treated it as a ranking problem. And this is probably because I've done a lot of my research in recommender systems, which is about ranking. So I kind of think about the world in that way. And so we basically wanted to come up with a ranked list of candidates. And then we did that by using the high performer imputation. And then, but what we noticed about a list like that was that it was imbalanced in terms of the adverse impact ratio. And so we ended up swapping the sort of lower realms of that candidate list with items that we predicted as being also, good candidates, but ones that we predicted as being in the protected group. And so that enabled us as a way to kind of balance the membership to get the adverse impact ratio pretty good, but also retain that top piece of the candidate list that we knew was going to hit the high performer targets. So that was kind of where we ended up. And the way we got there was to do what a lot of the other teams have already talked about, sort of model the outcome variables separately, high performer, retained. We also did model protected group as is required by this kind of ranking model. And then we had this kind of a sequence of applications in ranking in order to produce that final set of lists to hire. Okay, next slide. And there's a lot of detail here. I'm not gonna go through every line in the slide, but one of the things we noticed about this problem is it's not really a big data problem. It's really an ugly data problem. And so we, again, like a lot of the other groups that we've already seen, imputing missing data was very important. Transforming the data was very important. We looked at these distributions of things, saw the big skew in the time variables, for example, and realized that a log transformation made sense there. We looked at basically tried to find correlations between the different variables that were there, but as other folks have noted, there wasn't a lot that you could get out of some kind of compression or PCA analysis. We did do some feature design. In situational judgment, we made the assumption that basically the most popular response for the situational judgment items was the right one. And so basically then we were able to turn that into a simpler variable, where somebody either got that right or got that incorrect. And then we just did a lot of feature combination to kind of in a manual way rather than a sort of PCA kind of way to reduce the dimensionality of the input data. And then when it came to modeling, we tried a lot of different things. I mean, I think we can, would be a long list if we list out all the different kinds of models that we tried. And ultimately, I think like some of the other groups as well, we realized that simple models worked just as well as the things that took a long time to train. And so the value of being able to do something quickly, there wasn't a lot of added value in doing the things that were sort of fancy machine learning things. And so we ended up using an elastic net regression, basically, to do that. And we built models for each of the three different things: retained, high performer, and protected group. And one of the things I want to say about the protected group issue in the course of predicting that, it turned out to be quite difficult to predict that above the baseline, but it turned out to be actually pretty important to do that. And although that seems maybe a little bit counterintuitive, as some of the other presenters have said, it's actually a pretty common finding in fair machine learning that that you actually can't be blind in a case like this. We recognize that there are actually biases in the data that comes in, and that if you're not actually aware of individuals' protected group status, then you're at the mercy of the biases in the input data. And so rather than try and tease those out, it just made more sense. And again, this is a finding that's pretty common. It just makes sense to use that data when you have it and try and impute it as best you can when you don't. All right, and then I think Goran is up next.
All right, excellent. So here in this slide, I'll provide some little additional details with respect to what we did. So we modeled each of the three focal outcomes: high performer, retain, and protected group individually. So we treated this as a univariate machine learning problem. And we use these elastic nets for each of those outcomes. Now, when we were tracking how well our elastic nets are performing, we used the typical kinds of statistical measures that are used: specificity, sensitivity, accuracy, area under the ROC curve. And but I want to especially point out the J-index. The J-index is a nice and simple one, which simply is the sum of specificity and sensitivity. So the reason that's important is you needed to be right both in terms of correctly identifying those who would be high performers and also correctly identifying those individuals who would not be high performers. We discovered that models that were good at that, essentially that were maximizing the J-index and not just simply maximizing specificity and sensitivity, were the ones that were giving us the best kind of overall scores. So what we did first was we heavily focused on training the high performer elastic net model. And initially, the way we worked this out on the development data is that we can develop an elastic net high performer model and rank order each of the possible candidates that we might hire from highest to lowest probability, and we would select the candidates with the highest 1,125 high performer probabilities. That's the number of individuals that we had to hire out of the 2,250. And so on the test set, on the final set where we only get 5 submissions, simply doing this kind of selection gave us a score of 59.3077. Now, this exact same procedure in the development set landed us a score of 55, which isn't that great, but we were encouraged that we got such a high score to begin with at 59.3077. Now, the wonderful thing kind of about this competition, maybe for the wrong reasons, that it was extended for an additional year due to COVID, but Nick and Isaac also gave us an additional 50 submissions on the development data set. And that gave us an opportunity to learn and think a lot. And you can tell that all the groups, all the individuals presenting today love to think. So thanks, Nick and Isaac, for that opportunity. So there's a really good time to think about this for an additional year. So that allowed us to learn, for instance, that in these models that we built for high performers, how they perform. And we learned that, for instance, certain types of elastic nets would be way off on the adverse impact ratio. They would be too low, 0.8, whereas certain others ones would get closer to the optimal value of 1.0. And in particular, we were able to find the right sort of tuning parameters for elastic nets that would land an AIR somewhere between 0.94 to 0.98. Now, this was fundamental for our approach because, and at that point, we go on to the kind of our second stage of our modeling system, which is to then cut into the 3D dimensional space of high performer, protected group status, and retention, and swap out the individuals with some of the lowest high performer probabilities that we initially hired, and those individuals also that had low high performers and low protected group probabilities, and then swap them out for individuals that also had kind of low high performer probabilities, but they had higher protected group status probabilities and higher retention probabilities. So this swapping process landed us our final score of 62.5. And you can see that the swapping process in itself was fundamental and increased our score by about 3.19, 3.2. So this was a multi-stage selection process. It was very important to get a nice trained statistical model to perform well, but then also have a selection system underneath that to maximize our score. And Ian, please, next slide. And so here we want to highlight kind of 4 thoughts that we have based on this competition, based on the solution that we came up with for the field to think about. Now, someone already mentioned this. I want to say a great job to Isaac and Nick coming up with this scoring algorithm to score our submissions. I thought it was really clever and a really nice demonstration of using not only statistical measures to evaluate how well models perform, but also something resembling a practical measure. Now, the scoring algorithm was in part based on statistical measures, but it absolutely punished anytime there was unequal selection ratios for the protected group and the non-protected group. So this was really, and that was a really cool aspect of this competition. And it's something that always bothers me when I read our academic literature and we get to the practical implication section and none of these kind of calculations are done. There's just words being written and like, no, you're just talking right there. You're not giving me anything. All right, now number 2, we started this problem thinking about it as a multivariate problem. Can we simultaneously optimize the 3 outcomes? Okay, so we initially tried to treat this as an 8-class classification problem by combining high performer, retained, and protected group, but this did not lead to good overall scores. So it was interesting that a kind of a univariate machine learning approach with a multi-stage selection. So it was kind of a sequential, maybe multivariate approach. I would describe what we did ended up being best. So I did some reading, and our team did some reading about multivariate machine learning, and it seems like an area that needs to develop further, not just in IO, but in computer science and beyond. So I thought that was interesting. Number 3, this comes from some of my own modeling experience of IO, psychological variables, OBHR, the things that we measure typically in selection and when we observe employees in the workplace, is that our psychological measures may not be that great at picking up interaction nonlinear effects to any meaningful predictive degree. So we know that interaction effects in our literature are generally notoriously small. So is the problem the concepts that we have or the way that we actually measure those concepts and ideas? I think it might be the latter. So what we found was that any of these algorithms, models, machine learning models that attempted to capture those interaction effects did not really lead to any greater success. That's why we stuck with a linear model like elastic nets. And furthermore, when we introduced manually constructed 2-way and 3-way interactions into the linear model, like you would for a typical ordinary least squares regression or logistic regression, that itself did not provide any additional predictive power. So interaction effects from our analysis were missing in this data, and I think it's representative of the types of measures that we use that cannot pick up on those kind of interactions that might actually exist, that might actually be present. And lastly, I'll point out that something that is absolutely key, and as Nick, as you were presenting, that you saw that there was a change in the scoreboard from the public leaderboard to the private leaderboard, the rank order of submissions, who was top score and who was bottom score and so forth, changed a little bit. because you want to have models that generalize. That was kind of the overall evaluation of this competition. And in our field, on the academic side, but I know Nick and Isaac, the two of you were saying the other day, that even in practice, we don't often spend time evaluating our models on holdout sets. How well do they perform beyond the data that they were fitted on? I think this is absolutely critical. And do I need to mention for psychology, replication crisis? Do you think this might be one reason why we're experiencing that? So I think we need much further testing with respect to how our models generalize beyond the data that we're fit to. Okay, and I believe our last slide is just a thank you to the organizers, and we'll leave it there. Thanks for listening.
Wow, thank you. That was incredible. What interesting insights. Yeah, the real competition is these participants that struggled with this data for sometimes years, like Axiom, and wrangled and came to thoughts that we as a field now have to grapple with. Thank you for sharing, Goran and team. All right, for our final #1 position, returning champ, Feng from Bowling Green State University.
Thanks. Can everyone see the PowerPoint slides now?
Yep.
Thank you. Okay, so first, big shout out to Isaac and Nick for hosting the competition. It's a lot of work. Without them, this would not happen. And we also want to thank Walmart for providing the data so that they are not allowed to participate this year. That's the only reason we can snap the first place this year. All right, let's. Okay, so as some of you knew, we participated and learned a lot from the last competition back in 2019. And actually, we had a joke that having a good computer is a key to win. Apparently, we did not improve on that part. So, but for this year's competition, building on some previous experience, we have some general guideline before we even start. So we aim for some like simple, stable solution. Make sure we run more cross-validation and use the ensemble model. And next, we agree to practice good time management. Everyone is busy and we want to make sure to make best use of everyone's time. That means less meeting and more effective communications. And for later, we share the code using the Google Colab. We found it's very effective that everyone can keep up with some new updates. For this presentation, we decided to discuss our solution by following the project timeline, so that for people who are not familiar with machine learning, can relatively easy to follow. And as you can tell from here, in 2020, we spent around, like, in sum, 2 weeks for the competition. Then 2021, 3 days before the deadline, as our team name suggested, we procrastinated a lot. And so basically we spent 3 days this year for the competition. Okay. So for the week 1 last year, after a brief meeting about brainstorming the project ideas, what direction we want to go, what methodology we want to try, most of the time actually we're spent on getting to know the data. So really, we spend a lot of time just mostly they are just some routine practice here, but we found they are extremely important. So for example, the intercorrelation and also some of the base rate for the criterion variable, and actually they can give you enough information for you to start building a model. And it is equally important to understand and study the metric, as some other teams already mentioned. So this is really not a statistical evaluation metric, but it's more practical. And by studying on that, we knew that the cross-validation definitely like it's necessary, and it is difficult to build a stable model. And one thing I do want to emphasize here is that we also build our own customized evaluation metric from the day one. I think that's pretty handy because this evaluation metric is not the traditional one, right? So we build our own for the cross validation, and I think that saved us a lot of the time just by having that. So I strongly recommend that. Like some other teams, so our basic strategy is we try to train multiple distinct models to best predict the distinct component from the evaluation metric. Specifically, we try to predict top performers, top performers and retained and protected groups respectively. Then by studying our metric scores, then we try to build a simple weighted model to start with. Here for the feature selection, basically we try to include all the features we use to train the model. And for the missing values, we try the various methods for the imputation, and also we create additional features based on the proportion of the missingness. And but that did not further improve the model. And also, like, we tried the additional data have the turnover information, that also did not further improve the model performance. So final training data set is a relatively small sample size with less than 7,000 rows. So for the final model, basically we had for every distinct model, we apply the XGBoost. Most of you nowadays are very familiar with the XGBoost model. It is improved version of the gradient boosting with higher computation efficiency, but can better deal with the overfitting problem. Another important reason is like we were lazy. So, you know, the XGBoost not only powerful, but also can automatically deal with a missing value to start with. So we just start with that and it worked well. We also tested, I believe we spent half day to test some like a deep learning model, a very basic linear perceptual model, but no improvement found there. And for the criterion variable, we kept the high performer overall rating and protected. And also regarding the cross validation, I want to quickly mention one thing. It's like after a few days, we realized like in the very beginning, we applied just the default split function from the Python library. And then we realized, oh, we should run the stratified random sampling instead. It's a very trivial thing, but a huge mistake there. So summary for 2020, we made 9 submissions totally with the best score of the 60.5. And by studying our like metric from the cross validation, we knew like we cannot just combine every component. That's not working. So instead, the idea behind it really, we first try to select the top performers, then adjust by the workers from the protected groups. And by now, no fine-tuning for the XGBoost model yet. And the cross-validation, of course, clearly suggests that the solution is not that stable, and the unfairness score really matters. Then in 2021, this year, so 3 days before the deadline, we try to pick up this task. So mainly we are trying to solve 2 questions, right? So the first one is how to better adjust the unfairness score. We have some idea, but the one we decided to go with is, instead of predicting the workers from protected group. How about we predict workers who were from protected group and also stayed within the organization? The cross-validation did not suggest it performed better, and also the stableness is similar to previous model. However, the weight from this approach, you can assign a slightly smaller weight. So that's why we decided to use this as a base model. Then, of course, like we have never fine-tuned the hyperparameter for the XGBoost model yet. Here we apply the Bayesian hyperparameter optimization technique. So basically, we just try to adapt some code from the Kangol forum, and it took 6 hours alone to just simply tune one model. So it's something. Well, so for our final winning model, so it is ensemble model from 4 distinct XGBoost models, but you can tell that the first 3 distinct models they are all used to predict the top performers. Okay. Specifically, the model 1 and model 2, they are the prediction model for high performer. The difference is a default and a fine-tuned model. The model 3 is the prediction model for overall rating. And the last model 4 is the prediction model for people who came from the protected class, also from the retained the group. And the final selection basically based on the ranking of the predicted final z-scores, which are the weighted like the score from those 4 distinct XGBoost models mentioned above. Okay, so some lesson we learned this year is, yes, you want to make sure you use the ensemble model, and also some other teams already mentioned, the simple solutions can be good solution. Cross-validation is important, and we realize this solution is very sample dependent. So yeah, we wish we have more time to try some like new techniques to reach a more stable solution. And last, again, it's always a great opportunity to apply some machine learning techniques to tackle real problems. And also, we did not include some important features because that does not make too much sense. So how to integrate the model, that's another huge challenge in our field. And last, I want to thank some of our lab and team members, like although they were not involved later for this project, but we have exchanged many ideas. They gave us many good insights and feedbacks. Thank you.
Awesome. Great. Thanks, Fang. So that's the 4 teams winning solutions, their strategies and their thoughts. We'd like to kind of open up a panel discussion for the winning teams. We have a couple of questions, and happy to hear questions from the audience as well.
Yeah, awesome. You know, some of these were already covered in depth in the presentations. And again, huge shout out to you guys. Amazing work. Thank you for presenting it. Thank you for thinking about it. Thank you for taking it seriously and contributing your knowledge to the field. I think the most interesting question to me is that third one, which is race on the prediction side. A lot of you guys used race predictions on the prediction side. We don't usually do that in the field. Should we be allowed to do this? What are the pros and cons? What are the ethical considerations and the legal considerations? Yeah, I'd love to hear your thoughts.
I'm happy to jump on that one, maybe because I'm not in organizational psychology, but you know, one of the things that I think is a finding from you know, from fair machine learning more generally, as I said in the presentation, the reason why we end up with biased outcomes is because folks are in situations that are different, that our society has discrimination. The result shows up in any kind of variables that you might be able to collect about people, the fact of kind of what's considered normal, what's considered a baseline, and so forth. All of those things reflect the discrimination that's there in society. And so it's very difficult to say, okay, we're going to fix that, but we're not going to look at the thing that's the causal, link, right? It's like that's just that just means that you have to re-impute that variable from other things that you gather. And so I think there is a good argument to say, let's use that information directly, provided that what our goal is like the goal here in this competition, which is to say, we're striving for a certain kind of cohort of people that we're going to hire. We want that to look a particular way, and so we have to, we want to do that in a way that gives us good employees. But we also have to be sensitive to the fact that the data we're using to make those decisions has its own biases, and so we have to fight those.
But wouldn't that fall within kind of like the affirmative action bucket?
I'm not afraid of the word affirmative action. I think that actually what that really means, what that means in practice is just this recognition that, the things that we might measure are things which are conditioned on, existing structures in society. And so, I think rather than affirmative action, I would say, we're recognizing the fact that out there in the world, the starting line for the race is not the same for different people, and so it's no surprise that they don't cross the finish line in the same time, and so we have to take that into account.
Right.
I think. Oh. Well, one thing I was going to say about your solution, what's so interesting is like it's almost like the measurement error itself. You're swapping in folks that would fall within that measurement error would be equal without that error, and you're saying, hey, I'm going to pick the diverse of these two that are
right. And part of that's of course driven by the metric, but I think there's a good argument to say, there's so much uncertainty in the things that we measure. If we have some hard cutoff, we're sort of we're arbitrarily asserting a difference between individuals, which really within the boundary of the kind of measurement or even prediction error of the algorithm, they're really the same. And so randomizing around the boundary is actually something which is well understood as a fairness technique in fair machine learning. And so that's kind of what we did. We didn't actually randomize, which one could do, because we want something a little bit more predictable. But given how difficult it is to predict protected group and some of these other things, it kind of has that element to it.
Yeah, I'll call what we did our swapping, our second kind of stage, multi-dimensional because we used all three outcomes to do the swapping, including high performer scores, multi-dimensional banding. And so Isaac, to your point, that indeed we said, okay, well, these lower high performer probabilities and these other lower high performer probabilities, they're within a band, right? And so now we're going to just swap out for these other outcomes that we care about, that we want to optimize given the scoring algorithm.
One of the things that I noticed, and I think that as the field we kind of ignore, is the fact that it seems like the teams were pretty effectively able to make predictions on the protected group status. And so like one could argue that in a traditional selection system, we might not actually have the information available of their protected group status as part of the selection system. Now, the applicant tracking system probably would, but as part of the selection tool, we might not get past that. But it was just kind of interesting to me that it seems like all the teams were pretty effectively able to predict protected group status just from their response patterns and the items to the point where they could infer that as part of making a more fair selection system, which I think is something that as a field, it seems like we kind of ignore the fact that those response pattern differences are embedded into our assessments.
All right. I'll just add that when it comes to predicting race in the models, I kind of got into this during my presentation, but as someone who hasn't been in practice, it strikes me as kind of arbitrary that we don't want race in the model, but we're okay using race outside of the model to evaluate our model. So like, is the incorporation of race or protected group, like, why is there that boundary there is like my question. And I think if there isn't a good reason, we're kind of hamstringing ourselves unnecessarily.
Yeah, I think Josh and Nick, to both of your points, this, by excluding race, that doesn't mean that race is no longer present in the data by just excluding that explicit variable, right? And the fact that we were able to predict this protected group class so well, and it was such an integral part of almost all of the winning solutions, indicates the fact that there is a difference in signal here, right? There are differences, there is variance in the data that is captured by this protected group status. And if we ignore that, we actually come out with a model that is both less predictive of sort of high performers, but also is less capable of addressing these pattern data because it's just treated as a random pattern as opposed to understanding where that linkage is in the data. That's at least why we approached the problem the way we did.
There's some great questions here. If I may touch on something that I mentioned during our presentation, measurement cannot be ignored. Okay, so statistical modeling and all that comes after the data collection. Okay, statistical models, all they can do is squeeze out, optimize the information gathered by your measures. Modeling comes afterwards. Data collection comes first. Okay, so there's many decisions you need to make when you develop measures. One is, well, what are we measuring? Two is, how are we measuring it? And three is, who's making decisions on what is what on a measure? So for instance, giving a shout out here to Mark Fogel, his question in the chat, which is, well, how do you define high performer and who's deciding what high performer is? In this data set, there were differences in the proportion of high performers for the protected and non-protected group. Small differences, but they were present there. Now, is that really in an objective way because the one group outperformed the other, or is that part of a measurement issue in that, well, you have a preconceived notion of what high performers look like and what they do, not just what they look like, surface style, but what they do that contributes to work. We need far greater thinking about what is something that resembles performance. And to Robin's point earlier, that that requires I would say more detailed, at the very least, job analysis. It's not just simple. It's not easy enough. It's not just about listing out the knowledge, skills, abilities, personality characteristics you need to perform the job, but you also need to see what actually contributes to work processes that are helpful to achieving organizational objectives and goals. So I'll stop there.
That actually, when you made that point in your presentation, I pinged Isaac with that, because I think that it's almost like we want our assessments to be so fine-tuned. We only have so much time, and we want to get so much information out of it in such a short period of time that we actually almost want discriminant validity in our measures, right? We want them to be completely unique from each other, so they're potentially getting at this different part of the criterion space. But like you mentioned, that could have impacts for the ability for interaction effects, because they're all so different from each other. Maybe that interaction effect isn't there, and so it could hinder our ability to leverage the power of nonlinear models. It's a very interesting concept. I'd never really thought about it like that before.
Yeah, go ahead, Josh.
Oh, I was just going to add something short to Gordon's statement about the criterion problem. We had taken those 8 extra criterion dimensions and tried to predict high performer from it. And I don't know, we got an R squared of 0.5, which is pretty high, but with 8 unique measures of what high performance means to not, I don't know, I guess we thought we were going to predict it better. So like, what else was impacting who was classified as high performer or not, I think is a open question that Gordon kind of raised, and I think it's a good one.
That's an excellent question. And man, it's been a year and a half since we did it. I'd have to dig back in. I think if I remember correctly, we didn't give you the actual variables that we used to calculate high performer. So there was probably like 10 or 11 supervisor ratings of criterion, and we kept those out because we didn't want you to be able to perfectly reproduce high performer. But we did give you other ones that were related to them to see if you could use them to squeeze some more signal out of the feature space. I'm 95% sure that's what we did. Because to your point, if we would have given you those, you could have perfectly recreated it. And I believe that those were on a 1 to 7 scale. So then you have a little bit more criterion information. And in a natural competition where you're trying to make predictions of new individuals, you wouldn't have necessarily had that information. It's kind of what our thought process was on the competition front.
Nick, you did include that information. And here, very quickly, I just want to add one thing regarding the measurement. So I noticed, like, from our competition is that most of our solutions, we definitely rely on the item level information, right? One interesting I noticed from this setup is there are a couple posters and also symposium also talk about the how we can just tackle the measurement validity issue from the item level versus the scale level. I think nowadays with the development of the machine learning, that's one thing I think in our field we should also pay attention to. Yeah.
Absolutely. Yeah.
It's just so insane to me. I would have never expected from putting this data out there that we would come to really heads with some of our legal constraints, where maybe they're antiquated and against really the possibility of making it completely fair. And I think that's kind of the informed conversation that I hope continues after this. From this, code, let's talk more action, so that we can have a real informed question, like how much does fairness matter, and what are we willing to sacrifice in our ivory tower of measurement to acknowledge the error, maybe even where we could make true algorithms that have a 1 in the adverse impact ratio, which was the basis of this and all of you guys achieved.
Yeah, one thing I was curious about from all the submissions that came in was fairness an obstacle? Like, was it an obstacle to a better system? And so what I did was I actually created bins of the ones with the most adverse impact and the ones with the least adverse impact. And then I looked at the distribution of the true top performers, true retained, and the intersection. And it ended up being where the most fair were actually better than the least fair. So in this instance, it actually was that being fair didn't penalize your ability to predict important outcomes of interest.
Yeah, I think since we're about at the 12:30, I think, Nick, do you want to wrap us up?
Yep. These are some thoughts that we came up with from having a discussion with the winning teams about a week earlier, and then from looking at kind of how they use it and what their codes look like. And I think this has been mentioned by just about everybody: cross-validation, cross-validation, cross-validation. I don't think our field does enough of it. I think that we're starting to do more of it, but I think that we tend to think that purely linear models, it becomes pretty difficult to overfit. And I think to a certain extent, there's a little bit of truth to that. But as we move into these more complex algorithms, cross-validation becomes even more important. What I noticed and Isaac noticed is the pros of a multidisciplinary approach. This year, it seems like a lot of the top teams had individuals that were not strictly IO psychologists on their team. So can we collaborate more with people in other fields to solve some of these problems? machine learning competition basis for continued innovation. So, let's keep up these types of competitions. Like Isaac mentioned earlier, a couple of years from now, we can still do an apples to apples comparison on this data. I know that since the 2019 machine learning competition, things like ULM Fit and Roberta have come out. And so I've had fun testing those new methods on that data to see if it improves on what happened in 2019. Fairness and perfect fairness, an adverse impact ratio, a selection ratio of 1-to-1 is possible, but what do we need to do as a field to realize it? Like I mentioned, the most fair results outperform the least fair results on all of our criterion this time. As all of you guys have mentioned, and Isaac mentions, like ethical and legal and algorithmic concerns. Can we start to explore, trying to include that protected group status to help balance out and make the algorithm itself actually fair for all groups? Nonlinear complex models seem to outperform basic models. That happened in 2018 as well. Again, I think that's just more evidence that machine learning has value in our field. And tools that are built to focus on fairness didn't necessarily win the competition. I know that a lot of people started out with multivariate outcome optimization in mind, and can we balance all of these together to produce the best scores? And in the end, it seemed that most of the teams fell back on these univariate models, and ensembling them together is what created the winning solutions and the best solutions. So that's kind of interesting.
Awesome. Thank you, everybody. Thank you for participating in this year's competition. It wouldn't be a competition without the community. So thank you all.
Yeah.
And congratulations to these winners.
So,
You guys
thank you,
killed it.
and
Thank you.
everybody who participated.